Good afternoon. Before we begin our Unit 1 review for the AP Chemistry exam, we are going to go over solubility product and molar solubility from Chapter 17, Section 5. All right, so problem 1, we're going to write solubility products for these ionic compounds. Let me go ahead and do them over here. Okay, so barium fluoride is our first compound, and it is going to dissociate into barium 2+ and fluoride 1-. Because the fluoride is a halogen, it's going to have a -1 charge, so I need 2 of them to neutralize the 2+ charge. So I will need a coefficient of 2 there. That means when writing the solubility product, which is just like any other equilibrium constant that we've learned, the products, their concentration goes on the top, the reactant concentration goes on the bottom. In this case, the reactant is a solid, so it is excluded from the solubility product. So we have barium 2+ and fluoride 1-. This coefficient, just like every other equilibrium, is the exponent now. So that becomes fluoride squared. And that is the solubility product of barium fluoride. Calcium carbonate, also known as chalk, is going to dissociate in water to form calcium. Whoops, let me switch my pen out. Calcium 2+ ions and the carbonate ion 2-. The KSP will then be the concentration of calcium times the concentration of CO3 2-. And it's not very pretty. Okay, for the next one we have sodium fluoride, which is going to split into Na+ ions, aqueous, and F- aqueous, and they all have a coefficient of 1, so the KSP is simply going to be Na+ times F-. And that's brackets for concentration, which are important because that implies that those are in molarity. All right, then we have iron 3 hydroxide. We can deduce the charge on the iron because there are 3 hydroxides and every hydroxide has a -1 charge. We need a +3 on this iron to balance out that charge. And the 3 hydroxides that it forms over here mean that the KSP is going to be iron 3+ times hydroxide cubed. Lead iodide dissociates into lead 2+ in this instance because iodine is a halogen. It's going to have a -1 charge, and therefore you need 2 of them to balance the charges. KSP is going to be Pb 2+ times I-, and that is squared. And last, lithium sulfide, solid, ionizes to become Li+. There are 2 of them, aqueous, and the sulfide has a 2-, and that is also aqueous. KSP is Li+ squared times S 2-, and that is the first problem. For the second problem, it says, look at the solubility table. Which ions are generally insoluble? Listed as S for solid. So if you Google Flynn, 2 N's, solubility table, you will get a table that looks like this, but is color-coded. And it's very useful in determining which compounds are going to be soluble and which are going to be insoluble. So looking at this, you can see that almost everything in this area is soluble. So that means that, especially down this row, these are all soluble. So ammonium, lithium, sodium, and potassium, which are all group 1, we have ammonium, and then we have group 1 elements, are all soluble. There's one exception here, but for the most part, you can say safely that these are soluble. Group 2, it's about 50-50 soluble versus insoluble, so we'll cover those in a second. And then we have some transition metals that it would look like these are mostly insoluble. Okay, going across the table, we have a few patterns of these are mostly soluble right here. So these would be our halogens in group 17. And coming down here, I see a lot of insoluble for the hydroxides. These are all insoluble or partially soluble. Carbonate, phosphate, and chromate is pretty insoluble. Sulfate is about 50-50, maybe a little bit more soluble than insoluble. So if we wanted to summarize those, we could use our NAGSAG rule, which says that the nitrates, those were always soluble no matter what you put them with. Same with the acetates. Group 17 is almost always soluble. So those halogens are almost always, with a few exceptions. Same with the sulfates. There's a few exceptions for sulfates being soluble. Ammonium, they are all soluble. And group 1 is all soluble. Okay, so down here, these are things that are insoluble from the table. Hydroxide, sulfide, carbonate, phosphate, chromate. These are the negative ones that were tended to be insoluble. Calcium, barium, silver, lead, and mercury as the positive ions, the cations, tend to be insoluble. And an easy way to remember those is our Castro-Bear, which is calcium, strontium, barium. Strontium is not on there, but it tends to be insoluble. So these with the sulfates are insoluble, as well as the group 17. And then our PMS, our lead, mercury, silver, those ions tend to be insoluble. So if you see these ions, most likely they're going to be insoluble. Okay, so that wraps up number 2. Number 3, state whether the compounds below are generally soluble or insoluble. So using those rules, I'm going to write S for soluble and I for insoluble. This is ammonium, which we just said is always soluble. So despite the fact that it's with hydroxide, ammoniums are always soluble, so we know it's soluble. This is a group 1, so that's going to be soluble, as well as this is a halogen, which is usually soluble, so that one's definitely soluble. Nitrate is soluble, and this is nitric acid, which we know as a strong acid, meaning it ionizes completely, so definitely soluble. Nitrates are always soluble. So lead tends to be insoluble, but in this case, when we put it with nitrate, it becomes soluble. So that's a tricky one. As is barium fluoride. Barium tends to be insoluble, but fluoride is a halogen, which is soluble. In this case, if we look at our table for barium fluoride is slightly soluble, so that is not clear cut on here either. So we will write slightly soluble. Calcium carbonate is an easy one because this is a group 2 and it's a carbonate. It's going to be insoluble, and this, as we mentioned earlier, is chalk. So when we put it in water, we get a opaque, chalky, not clear solution, meaning that there's a lot of solids that have not dissolved, so it is insoluble. Sodium fluoride, that's a group 1, soluble. Iron hydroxide, this hydroxide tends to be insoluble, and the iron is a transition metal, which makes it doubly insoluble. Lead iodide. Lead tends to be insoluble. Iodide is a halogen, but the fact that this is lead makes it insoluble. And this is actually that bright yellow precipitate that you can see if you Google lead iodide. It goes from clear solutions to a bright yellow precipitate. So that is insoluble. And that's one you might want to look at. Iron nitrate, it's a nitrate, so it's going to be soluble. The chloric acid, because this is chlorate, not hydrochloric, which is HCl. This one is also kind of a tricky one. It is sometimes considered a strong acid, sometimes not. The Ka value is what we would have to refer to for this one. So if Ka is greater than 1, then we can consider it a strong acid or soluble, which when you look it up, it's very hard to find the Ka value of this. The pKa is about -1 to -2, meaning that the Ka should be between 10 and 100. So I would say that's safely greater than 1. I'm going to say that this is soluble. Okay, so that is soluble. Carbonic acid for sure is a weak acid, so it ionizes less than 5% or about 5%, making it considered insoluble. Potassium sulfide. Potassium sulfide is group 1. So despite the fact that this is a sulfide, the group 1 potassium makes it soluble. Zinc sulfate. The sulfate with the zinc, let's refer back to the table so we can check our work. Zinc is a transition metal, the last of the transition metals. And sulfate down here, it is in fact soluble. So that is kind of a tricky one. If we had it with lead, it would be insoluble, but the zinc with the sulfate is soluble. And calcium sulfide, that's a group 2 with sulfur. That one is going to be insoluble. Group 1, that makes us soluble, but also this is acetate. This is sodium acetate, which is definitely soluble. Silver nitrate. So the silver tends to be insoluble, but all nitrates are soluble. So this one is soluble. Sodium hydroxide is the strong base that ionizes completely. So that is soluble, and it's also a group 1 with that hydroxide. Lithium chloride. Lithium is always soluble. It's a group 1, so this is soluble. And same thing here, the lithium hydroxide is going to be soluble. So despite the fact that this is hydroxide, it's with a group 1, so that makes it soluble. All right, number 4. What is the common ion effect? Common ion effect is when you have an ion in solution. For example, if we were trying to dissolve some silver chloride, and it's going to form Ag plus and Cl minus. If we were to add something to that solution that has either silver or chloride, a common ion, that's going to affect this equilibrium right here. So the Ksp for this is Ag plus times Cl minus. And let's say that we added a solution of sodium chloride. This is going to completely dissociate and form Na plus aqueous and Cl minus aqueous. So if I put in 0.1 molar of this NaCl, I am adding to the right side of this equilibrium, and adding that chloride is going to produce more chloride ions that will then combine with the silver present, and it's going to shift this equilibrium to the left. So adding one of these ions shifts this left, meaning it's making more solid, making the silver chloride less soluble. So if we have a common ion in the product, that means that's going to lead to the salt being less soluble in solution. Okay, another example would be, let's say we have magnesium hydroxide, and that is going to form Mg2+ ions and OH-2 hydroxide ions. And if I were to add something that is soluble, let's say magnesium nitrate, MgNO3. So if I add magnesium nitrate to solution, I'm adding magnesium, which will shift this left, and less of the magnesium hydroxide will dissolve, so it becomes less soluble. Number 5, what type of compounds are affected by a decrease in pH? A decrease in pH actually means it's becoming more acidic, and more acidic means a higher concentration of H+ ions. So for number 5, we can actually refer back to this reaction. If I were to add H+ to this equilibrium, I have this solid, this is magnesium hydroxide, which is milk of magnesia. And if I were to add H+ to this equilibrium, it's going to react with the OH-. So decreasing the pH is going to increase the H+. Lower pH increases H+ or H3O+, which will then react with my hydroxide. And you can see, what is that going to do to the equilibrium? If I'm removing the hydroxide, then more of the solid can dissociate to produce more hydroxide ions on the right. So that's going to shift this to the right. So that means that if you have this basic ion being formed and you are lowering the pH, you're actually going to increase the solubility. Increased solubility. So to sum that up, we have the solubility of a compound with strong or weak. So this would be a strong base, strong or weak, weakly, basic anion being formed. The solubility of that compound is going to increase with increasing H+, or in other words, a lower decreasing pH. So the lower the pH, the more H+ you actually have in solution. So if you are releasing a strong base like this, or a weak base, as in the case of let's say you have, let's see, sulfide. If you're releasing sulfide as your negative ion, so magnesium sulfide could work. If you add H+ to that, this is going to act like a weak base. It's going to accept the hydrogen ions, and that is going to remove this from the solution, driving it to the right, making it more soluble. Or obviously we already did OH, or let's say you did carbonate. If you produce carbonate, like calcium carbonate, if we add an acid to that up here, then this is going to react with the H+, removing the carbonate from the solution, and you can dissociate more of the solid. So the solubility would increase and you'd produce more product. Okay, number 6, calculate the molar solubility of these 4 compounds. And then follow-up question, what is the pH of the saturated solution of these 2? So we can find the hydroxide concentration, and from there we can get to pH. So number 6, we have iron hydroxide, iron 2 hydroxide, dissociating into iron 2+ and 2 hydroxide ions. And the KSP for this, we have to look it up. It's in your book. It is 4.87 times 10 to the -17. Okay, and the KSP is also equal to Fe2+ times OH- squared. So from this reaction, how much is actually going to ionize, we don't know. So we can make kind of a modified ice chart. FeOH2, we're not worried about because it's solid, it's not part of the KSP. What we are worried about is how much of this ion will form. We can call it X. And then how much hydroxide is going to form. That's a Q. This would be 2X. Twice as much hydroxide will form as the iron 2+. So the KSP is going to be X times 2X, and this is also squared because the concentration is not only twice as high, but it's also squared up here. And that is equal to our KSP value times 10 to the -17th. 2x squared is actually 4x squared times x is 4x cubed. So to solve this problem, we are going to, that's my dog, divide both sides by 4. And we have x cubed then is equal to 1.22 times 10 to the -17th. And to solve for just x, since it's cubed, we need to take the cube root of both sides of this problem. And the cube root of that is going to be 2.3 times 10 to the -6. Add our units of molarity, and that is also equal to something we haven't talked about yet, which is called the molar solubility. So how many moles of this product will form? And it's just 1 mole. So how much of this will dissolve? This much, and that is the solubility, molar solubility. Okay, I'm going to do the follow-up for this, which is what is the pH of this? We know how much iron is formed, and we can figure out how much hydroxide is formed. So the concentration of hydroxide is 2x. So twice this, which is 4.6 times 10 to the -6 molar. And from there, I can find the POH, which is the negative log of that 4.6 times 10 to the -6, which is 5.34. So the POH is 5.34, and you guys remember that POH plus pH is 14, so pH is just 14 minus that POH, which is going to be 8.66. Okay, for iron 3 hydroxide, we have FeOH3, solid, dissociating into Fe3+, AQ, and 3 hydroxide ions. And the amount of S that's going to form here, 3 times that amount of the hydroxide is going to form, because there are 3 for every 1 iron. Okay, so for our KSP, which this one is a hard value to look up, I found a few different numbers, but the one that seemed the most reliable source, I think it was University of Wisconsin, 6.3 times 10 to the negative 38. Okay, so that means that my KSP is going to be iron 3+, which, remember, you always want to write out everything that you know how to do. So write out the KSP, write out the equation, just in case you plug the number in incorrectly, you'll get at least that point for writing it out. So this is going to be our S. This is 3S, and it's cubed, and that is equal to our KSP value. So this number would be given to you. Okay, 3S cubed, 3 cubed is 27, S cubed is S cubed, times S is S to the 4th power. Times 10 to the negative 38. Divide both sides by 27. That cancels out. S to the 4th, you have to take the 4th root of this. So on your calculator, you're going to have to use the button for the 4th root. And I got 2.2 times 10 to the negative 10, which is our molar solubility. You can call this X if you'd like, X and 3X. Either way is fine. It's still the concentration of the iron. And that's molar. And let's say that is the concentration of the iron. Let's define that, 3+. Okay, and then we have follow-up question, what is the pH of this solution right here? So the concentration of hydroxide is 3 times the amount of this one. So that would be 6.6 times 10 to the negative 10 molar. The pOH is the negative log of that. The negative log of that is going to be 9.18. The pH is then 14 minus that, 4.82. So this, yeah, this is a lot of writing. pH, as well as our solubility, molar solubility, are our answers because it asked us for both. So let's go ahead and box those in. So those are answers for that one. Okay, lead iodide is a little simpler. Lead iodide solid is going to dissociate into lead 2+ and iodide minus. And there are 2 iodides for every 1 lead. Okay, we are going to form S or X amount of lead and 2S, oh, there goes my dog, 2S of the iodide. KSP is lead 2+ times iodide squared. So don't forget to write that out and make sure people can read it. And that is S times 2S squared equals, okay, and the KSP value for this is in your textbook, and it is 8.7 times 10 to the negative 9. 8.7 times 10 to the negative 9, okay. So 4S squared times S is S cubed equals this KSP value. Divide both sides by 4. Take the cube root of that. So cube root. S is equal to 1.3 1.3 times 10 to the negative 3 molar, capital M for moles per liter. And that is really ugly. That's a 3. Okay, one more. Calcium carbonate. So our calcium carbonate, solid, some of it's going to dissolve in water to give off calcium ions and carbonate ions. And we have S, and this time it's a 1-to-1 ratio, since this is 2 plus and 2 minus. So we have S squared is going to be equal to our KSP. The KSP, so KSP Ca2 plus times CO3 2 minus is also equal to 4.96 times 10 to the negative 9th, and 4.96 times 10 to the negative 9th, square root both sides. Molar solubility of this is going to be 7.04 times 10 to the negative 5th power. Moles per liter. Always put those units, especially if the question says include units, because that is a hint that they're going to give a point for those units, and you will lose that point if you don't have them. Okay, number 7. Complete the following reactions. I'm going to go ahead and write right on this paper. Hopefully we can see it. And I'm not going to include what state of matter the products are in, because we're going to go back and do that for number 8. So all of these involve 2 ionic